Chapter 14 begins with an examination of the composition of seawater, sources of sea salt, and the processes affecting seawater salinity. Those physical differences from freshwater cause the unique varieties of life in the ocean that in turn have major influences on us on land. The word salinity comes from the Latin word for salt, but in science it refers to the ratio of the mass of all dissolved substances compared to the mass of the water. The average salinity of seawater is about 3.5%, but the salinity of surface seawater commonly ranges from 3 to 5%. For comparison, drinking water in the US can be no more than 0.1% saline, and the salinity of the Dead Sea is about 33 to 34%. By far the most common of the dissolved minerals in seawater is halite, or table salt. There are many other types of salts and other compounds found in seawater, and in fact all elements can be found there, albeit in very small amounts. In the early history of the Earth, the main source of salts in the oceans, and the main source of ocean water itself, was outgassing from volcanic eruptions. For most of the planet's history, including right now, the dominant source of salts entering the ocean is from the continents. However, even though the influence of material is continuing, the overall average salinity is not increasing. That's because dissolved materials are deposited in rocks and sea organisms at the same rate. Even though the average salinity is stable, the salinity of ocean water is not the same everywhere. Places like the mouth of the Amazon are less saline because fresh water is diluted in the oceans. Places where there is more evaporation than freshwater input, like the Arabian Sea, will be more saline than average. Salinity also occurs on a seasonal basis in some areas. In the Arctic, the ocean water becomes more saline in the winter because the ice being formed does not include salts. Once the summer melts some of that ice, the salinity then decreases. The seasonal differences at the North Pole, however, are disappearing as the amount of ice forming annually decreases as climate warms. More important for most ocean life is the pH of the water. This scale measures how acidic or alkaline a solution is. Your book and many others says that the scale ranges from 0 to 14. That's incorrect. Because it is a logarithmic scale, there cannot be a maximum or a minimum value. However, you certainly don't want to touch anything outside of that range. Oceans become acidic when carbon dioxide in the atmosphere dissolves in seawater to form carbonic acid. This has been a great asset in the fight against climate change. The oceans can absorb carbon dioxide, a greenhouse gas, instead of letting it remain in the atmosphere and causing warming. However, there's a limit to the amount of carbon dioxide that can be absorbed without harming ocean life. And we've hit that limit, at least for some organisms in some places. Any organism that creates a calcareous skeleton, and remember from last chapter's video that calcareous ooze is the most common biogenous sediment, will have its skeleton dissolved in acidic waters. If you eliminate large portions of the microscopic organisms, those with calcareous skeletons, that will have a cascading effect on the rest of the food web. Higher acidity also causes problems with animal respiration, growth, and reproduction. Corals suffer from ocean acidification because they have calcareous skeletons. They are also very sensitive to temperature change. We don't find corals at high latitudes because water temperatures near the poles are too cold due to the lack of sunlight. At lower latitudes, corals mainly live within 100 feet of the surface and very rarely occur below 300 feet because they enjoy the waters warmed by sunlight. From a depth of about 300 to about 1,000 feet, there is a relatively sudden change in temperature called the thermocline. This zone serves as a barrier to many organisms that cannot tolerate such a temperature change, either moving up or moving down. Below the thermocline and at any depth in the high latitudes, the water temperature is just a few degrees above freezing. Seawater density is determined by two factors: temperature and salinity. However, there are far greater relative fluctuations due to temperature, so changes in water density with depth, shown here as the pycnocline, only occur in the warm waters of low latitudes. Like the thermocline, the pycnocline is absent in high latitudes. Also like the thermocline, the pycnocline is a vertical barrier. In this case, it is a barrier to the mixing of upper and lower layers of water. In warm waters, a three-layer zonation of the ocean occurs. The surface mid-zone is warmest, with the most light, least density, and most oxygenation. The deep zone is the opposite, rich in sediments and nutrients, but low in temperature and low in oxygen. As a result, there is little mixing of organisms, or water, between the surface and deep zones. In the high-latitude Arctic Ocean, there is no such zonation, so surface and deep waters do mix. Instead of showing photos of the forms of ocean organisms by lifestyle habits, I think it is easier in this case to just create a list. The major divisions are where an organism lives, whether it moves, and how it moves. All organisms in the water column are mobile, meaning they can move. They are separated by how they move. Do they float along in the currents, or are they active swimmers? The floating plankton consists of the algae, or phytoplankton, and the floating animals, or zooplankton. These groups of organisms make up the bulk of the planet's biomass. Everything that lives on the seafloor is benthos, some of which can move, but some of which is sessile. Benthos is divided into the organisms that live on the seafloor surface, the epifauna, versus the organisms buried under the surface, the infauna. The distribution of marine life is controlled in part by the physical oceanographic factors shown here on the slide. In this case, your textbook does a good job of creating a table to simplify comparing terms. So I'll just remind you that there are three parameters to use to separate marine life zones: amount of light, depth from the surface, and distance from shore. The most unusual place to find marine life has to be the benthic oceanic zone. These are the deepest parts of the ocean. There's no light for more than 10,000 feet straight up. The pressure is more than 3 times that of a high-powered bullet hitting a solid, bulletproof object. Temperatures are always just barely above freezing. Yet some places at these depths and unusual conditions provide exceptions that allow worms like this happy guy to thrive. Hydrothermal vents brings water of hundreds of degrees to the seafloor, and along with that water are nutrients that microbes can use in the absence of light to create energy. These primary producers produce the energy used by more complex organisms like octopi, spaghetti worms, such as this one, shrimp, tube worms, fish, and crabs. I mentioned that our hydrothermal vents, primary producers use chemicals to create energy. Well, that's unusual. The overwhelming majority of primary producers at the surface use sunlight and photosynthesis instead. For that reason, most of the ocean's primary productivity is in the coastal areas because sunlight can reach all the way to the seafloor. The other controlling factor for productivity is the availability of nutrients. Coastal areas also have abundant nutrients washing in from the continents. Deep, warm waters tend to have very low biological productivity because the pycnocline prevents the mixing of nutrient-rich deep water with the oxygen-rich surface water. Now, this isn't a problem in the Arctic, where there is no pycnocline. However, the Arctic suffers from another problem. It only receives light in the summer, so there is just a brief period of intense productivity. Primary producers, in most cases, convert sunlight to energy in a very inefficient process. Only about 2% of the energy is incorporated. The rest is lost mainly as heat. Herbivores consume producers and are only marginally more efficient at the process, incorporating about 10% of the energy. Carnivores consume herbivores and likewise incorporate about 10% of the energy. This 90% loss of energy continues through higher levels as well. Therefore, it is more ecologically efficient for humans to eat as low as possible in this food chain. Unfortunately, people, including myself, tend to prefer cod and tuna over jellyfish and plankton.